Bismillahirrahmanirrahim. Uh, so let's look at this problem. Random variables L and T have joint PMF given below. Find the following quantities. Part A, expected value of L and variance of L. Part B, expected value of T and variance of T. Part C, covariance of L and T, the correlation coefficient rho LT. So before we begin to solve the problem, let us have a look at this giant PMF here. For it to be a valid PMF, all these values, all these probability values must sum together into 1. So for example, if you sum this 0.15 plus 0.15, this is 0.30, and plus 0.30, this comes out to be 0.60, 0.8, 0.7, and 0.8, and then plus 0.2 is sums it to be 1 as a whole. So this is a valid PMF that we have given, and we need to find out all these parameters from this probability giant probability mass function. So before we can find the expected value of L and expected value of T, we need to find their marginal PMFs from this given data, right? So marginal PMF of random variable, for example L, is given by T from all the sample values T. So P, L, T, L, T, capital, this is capital, L and T here, right? So we need to add all those probabilities values of T for a given value of L, right? So in other words, what it's saying is, for example, for this given value of L, we need to add all the probability values corresponding to T, right? So in other words, we need to add this row here. So this is 0.25, for example. We need to perform a similar operation for this one also. So this is 0.50 and this is 0.25. So this gives us the marginal PMF of random variable L, right? Similarly, we can find the marginal PMF for random variable T. To find the marginal PMF for random variable T, we can use a similar formula here, right? So now we need to add all those probability values for a given value of T, all the probability values corresponding to L. For example, this is the given value of T, right? And we need to add all the probability values corresponding to L here, right? So in other words, we need to add this column here. So this comes out to be 0.15 plus 0.15, this is 0.30 plus 0.30, this is 0.60, and this comes out to be 0.40. This is now the PMF of random variable T that we now have with us. So these are called marginal PMFs because these are written on the margin here, right? So that is why these are called marginal PMF. And one more interesting point is that if you add it together, for example, these probability values, these again come out to be 1. The sum is 1. If we add all these probability values here for this random variable L, the total probability value is 1, right? So let's summarize down the marginal PMFs that we have derived. So 0.25 for the value of random variable L is equal to 1 and 3, and 0.50 for random value for value of random variable L is equal to 2, and this is 0 otherwise. Okay, so this is the PMF of random variable L, and likewise we can write the PMF of random variable T. This is 0.60 when T is equal to 40, and this is 0.40 when T is equal to 60, and this is 0 otherwise, right? So these are the PMFs of the random variables L and T that we have derived. Now we can proceed to solve for the expected value of L and variance of L. So the expected value of L is given by this formula here. The expected value of L is also denoted by mu L, and for a discrete random variable it can be calculated like this. So L from sample value L and L multiplied by PL. So what it's saying is we need to multiply the value of random variable L with its corresponding probability value, and then we need to sum all such values together. So for example, we have this random variable L here. It has three values, 1, 2 and 3. So the probability value corresponding to 1 is 0.25, so 0.25 multiplied by 1. The probability value corresponding to the random variable value 3 is 0.25, so 0.25 multiplied by 3, and so on, and we need to sum them together. So expected value of L or mu L is equal to 1 multiplied by 0.25 plus 3 multiplied by 0.25 plus 2 multiplied by 0.50. If you add them together, so this comes out to be 0.25 plus 0.75 plus 1.0, so this is 2. So expected value of random variable L is 2, right? So now on to the variance. So the variance of random variable L, this is also denoted by sigma L squared, is equal to the second central moment of L. This is given by the expected value of L minus mu L squared, right? And this is also, this can be shown to be equal to the expected value of L square minus square of the expected value, right? So we already have calculated this. We just need now to calculate the second moment around mean. So second moment around mean, that is expected value of L square, is found similar to the value that we have found for the expected value. We just need to now multiply, we just need now to square actually the value of L before multiplying it with the corresponding probability value. So 1 squared multiplied by 0.25 plus 9 multiplied by 0.25 plus 4 into 0.5, right? So expected value of L square is 0.25 plus, let's use the calculator, 9 into 0.25, that is 2.25 plus 4 into 0.5 is 2.0, so that comes out to be this is 2.5 and this is 2, this is then 4.5, right? So this is the expected value of L square, the second moment around mean. So from here we can find the variance. So variance of L is equal to 4.5 minus the square of this value, which is 4. This is then 0.5. So variance of L is given by 1 over 2, right? So this is the variance of L. From this variance we can also find the standard deviation. So standard deviation is simply the square root of variance. So this is 1 over under root 2, which is 0.707. This is the standard deviation of random variable L. So in a similar manner we can find the expected value of t and variance of t. Expected value of t and variance of t, this is our next part. We have already determined the PMF, the marginal PMF of random variable t. So from there onwards the expected value t is easier to find. Mu of t, it is given by, we just need to multiply the value of the random variable t with its corresponding probability value, right? So 40 multiplied by 0.6, right, plus 60 multiplied by the probability value 0.40, and then we just need to add them together. So 40 multiplied by 0.6 is 24, and 60 multiplied by 0.40 is again 24, so that is 48. So expected value of t is 48, right? So now let's find the variance of random variable t. So the variance is given by, again we use the same formula that we used here for the variance of random variable L, right? So this is given by the second moment around the mean value, t minus mu of t, this is square, right? Second moment. So this is also equal to expected value of t square minus mu t square, right? So we already found mu of t, which is here 48, right? So we just need to find out the expected value of t square now. So for this we just need to square for the value of random variable t, 40 square multiplied by 0.60 plus 60 square multiplied by 0.40, right? So expected value of t square is given by 40 squared into 0.6 plus 60 squared into 0.4, and that is equal to 2400, right? So this is the second moment around origin, and the variance of t is given by this formula. The variance of t is equal to 2400 minus the square of the mean value. So mean value was 48, so 48 squared. So 2400 minus 48 squared, this comes out to be 96. So the variance of random variable t is given by this value, 96. So from here we can also find the standard deviation of t, which is 96 square root. This is 16 multiplied by 6, and this is 4, right? So this is the standard deviation of the random variable t. So the third part now, which is to find the covariance. So the covariance of random variable L and t, this is also denoted like this, is given by expected value of this function, L minus mu L multiplied by t minus mu t, right? And this is also shown to be equal to expected value of LT minus the product of expected value of L and expected value of T. So we already know the expected value of L, we already know the expected value of T, and we just now need to find out the expected value of this product LT here, right? So this is given by the same kind of formula that we used here for the expected value of random variable L and the expected value of random variable T. So this is given by, for example, the expected value of L T is actually a double summation here, right? So for example, so values of T corresponding to ST and values of L corresponding to SL, and we need to multiply the values of L and T and the corresponding probability value, right? So this is best demonstrated by doing it. So expected value LT is given by, for example, this is 1 and this is 40 here, and this is the corresponding probability value, this is 0.15, right? Then we have here 2, right, and the corresponding value of 40 here, and then this is the corresponding value of probability here, 0.30 for this pair of random variables L and T, right, plus 3 into 40 and the corresponding value 0.15, plus we have 1 into 60 and this value 0.10, plus 2 into 60 and corresponding value 0.20, plus 3 into 60 into 0.10, right? So we just now need to do this small arithmetic. So 40 into 0.15 plus 80, 40 into 2 is 80, into 0.3 plus 120 multiplied by 0.15 plus 60 into 0.1 plus 120 into 0.2 plus 180 into 0.1. So that comes out to be 96. So this is the expected value of LT, product LT. This is also known correlation. You know that this is also known as correlation. So this is the correlation of random variables L and T. But by no means does it tell that the random variable L and T are correlated or not. This is actually, this inference can only be drawn after we have calculated the covariance of L and T. However, we can tell that the random variables L and T are not orthogonal because this is a non-zero value. Had it been a 0, if expected value of the product LT would have been 0, then we could have said that the random variables L and T are orthogonal. If these are not, if the product is, the expected value of the product is not 0, then L and T are not orthogonal then. Okay? So let's now find the covariance of T here, covariance of random variables L and T. We can substitute these values of the values here. So covariance of random variables L and T. Sorry, this is not square. This is covariance, right? Covariance is 96. This here minus expected value of L was 2. And expected value of T, if you would remember, was 48, right? So 2 multiplied by 48, so that again is 96. So covariance of LT is 0. So L and T are uncorrelated. Note that the value of this correlation is not 0, but still the random variables L and T are not correlated, are uncorrelated, right? Because their covariance is 0. So similarly, we can find the correlation coefficient. So correlation coefficient is simply can be calculated using the covariance and the standard deviation or the variance values of random variables L and T. So for example, the correlation coefficient, sorry, rho LT is given by the covariance of LT divided by the variance of L multiplied by the variance of T, and this is square root, right? We can also write it here like this: LT divided by the standard deviation of L and standard deviation of T, right? So if the covariance is 0, then whatever is in the denominator will not matter much. So this is 0. So the correlation coefficient of the random variables L and T is also 0, which again means that the random variables L and T are uncorrelated. So you might think that this result is probably not what it should be. The number of pages and time taken must be correlated. Rather, they must be highly correlated. But if you revisit the problem statement again, then L is the number of pages 1, 2, 3. L is the number of pages 1, 2, 3, right? And T is the time to transmit one page, which is 40 seconds for text only and 60 seconds for page with images, right? So this time required to transmit a single page does not change whatever the number of pages, right? So L and T do not have any correlation, because this T here is the time required to transmit one page with text only. This T here is the time required to transmit one page with images also. So this time for a single pages does not change. It does not have any correlation with the total number of pages. The time taken for a single page always remains the same. So L and T do not have any correlation. However, if T would have been the total time needed to transmit all the pages, then that T would be highly correlated with the length of pages L. So this T is independent of this L. This T is the time taken for a single page only. This does not change how many pages do you have. For the time taken for the single page remains the same. So these L and T random variables are not correlated. These are uncorrelated.